Okay. Very well. So we left last week, last lecture with a description of the qubit. Now we are going to see the evolution. Before going to that, I would like to mention a point that is quite interesting about, again, the block vector. This is related to what is called the state tomography or state reconstruction. So remember I told you that to every pure state, we can write it like this. We can associate a unit vector that is given by this equation, right? So, and vice versa. If I give you this state, this vector, you know what state it is. One thing you can read from this is that by measuring these three average values, the average value of sigma x, the average value of sigma y, the average value of sigma z on the state, you can actually reconstruct exactly the state. So with three types of measurement, of course it's an average value, you need to do it infinitely many times ideally, right? You have to collect enough many statistics. But with three different types of measurement, you can fully reconstruct the state. So there are two interesting statements in what I've said. First of all, that you can fully reconstruct the state with enough many measurements, which is kind of obvious, right? The state should contain all the physical information about the system. If there were information in the state, in the mathematical object, that you cannot retrieve with any measurement, that would be useless, right? So it's normal that if you make enough many measurements, at some point you know everything there is to be known about the state. The second interesting point is that you need three here, not just one. If you were to sample from a probability distribution classically, it would be enough to sample from that probability distribution. Here, because the operators, their operators do not commute, these three guys do not commute, then somehow you need to estimate all of them in order to retrieve the state. You can't just estimate, let's say, sigma x. Very well. So this was just a side remark about, again, the role of the block vector and the correspondence between the block vector and the state vector. Now let's move to the main topic of today, which is the dynamics or evolution. Evolution for a qubit. And I will start with, again, the general algebra, not telling you exactly how a specific physical system implements that kind of Hamiltonian. We finished last time by noticing that every operator can be written in a given form that I repeat here for the Hamiltonian. So my Hamiltonian must necessarily be of the form something times the identity plus something else times one of the Pauli matrices, which I write sigma m, where sigma m, remember, it's just m times sigma. So in other words, and these are real, right? Because Hamiltonian is a Hermitian operator. So if you want, what I'm saying here is that there are three things that I need to give you in order to define fully an Hamiltonian. I have to give you E0, I have to give you the value E, and I have to give you the block vector M. This is true in general. Every Hamiltonian will be like that. An Hamiltonian that depends on time is one where some of these objects depend on time. Let's start with time-independent Hamiltonian. Then remember, we had this super important recipe we studied when we studied the evolution in general. Now we are going to be able to apply. Remember how it went? You have to find first the diagonalization of the Hamiltonian, the eigenvalues and eigenvectors. Then you have to write the state in the basis of the eigenvectors. And then the evolution of the coefficients would be automatic. Okay, let's go through it. Are we able to diagonalize this matrix? Obviously, yes. It's a 2 by 2 matrix. You can write it as a 2 by 2 matrix exercise. You can write it. You can try to find what are those numbers there. But I'm going to do it in a much more compact way. So we have H. I can also write it as, let's see what we have. Well, the identity is just, so it's, I know the eigenvectors of these, right? They're plus m and minus m. So this is E0 and then plus m plus m plus minus m minus m. this is the identity, right? And then plus E plus M minus M minus M. This is the identity, this is sigma M. So if I regroup the things together, it gives me E0 plus E on this vector plus E0 minus E on that vector. So here we have it, right? These are the eigenvalues. Let me call it maybe E plus, E minus, eigenvectors plus M minus M. So what I call the possibly difficult step in solving the Schrödinger equation here is trivial because it's a 2 by 2 matrix or because of these arguments, so it can always be solved. We have the diagonal form of the Hamiltonian. So now what do we have to do? Well, we have to take our generic state at time 0. This will be written like C plus M plus C minus M. Okay, we have to compute these guys. If you want a specific state that you have in mind, you have to compute these coefficients. But for me, let's assume we are able to compute them. Okay, so remember that this one is plus M psi of 0, and this one is minus M psi of 0. And if this is the initial state, remember the famous recipe. We know the state at time t, that is C plus will evolve with this energy, minus I E0 plus E T over H bar plus M plus C minus E minus I E0 minus E T over H bar minus M. And this is the whole solution of the Schrödinger equation. Now let me do a small trick here, just for you to see something that can be interesting. So I will take out a global phase. For instance, well, let's take out this one. Well, we could take another one. So I take out that number, E minus I E0 plus E T over H bar. Factor of what? Well, here remains C of plus M. Now here, I've taken out this number. This one is already out there, but this one I got a 2. Okay, so I get E, I, 2E, T over H bar, minus M. Okay, this is very nice. Why I say it's very nice? Let me show you. Well, first of all, we see something that we could have expected before, but if I would have told you, you wouldn't have believed. Okay, so this is a global phase. Huh? So it doesn't matter. This is the state. All that matters is here. This one we can take out at will. And see what? E0 is only in the global phase. Now, these we could have anticipated if E0 is time independent, because you see what it does. E0 is just an offset of the energy, right? All the states will be offset by energy E0. Now you know for classical mechanics and from essentially physics, right, that an offset on the value of the energy never matters. It doesn't matter whether here I call energy 0 the energy at the ground or energy 0 the energy at my head, because what matters is the difference in energy between these two situations, right? So we could have already expected that this guy actually does not play any very interesting role if it's time independent. If time dependent is a bit more tricky, right? Because it's as if you are changing the 0 of the energy with time. But if it's time independent, essentially we could have neglected that. Why I didn't do it? Well, pedagogically, so that you see that I could have neglected that. So E0 doesn't matter, as expected. Now let's see what is this. I mean, this function is a periodic function with period. So 2e t over h bar equal 2 pi would give back the same function. Would give back the same value, right? 2 pi n. So the period is given by whatever it is, right? But what matters here is that you see that the dynamics depends on 2e. What is 2e? Well, 2e is e plus, so e minus e. So let's go back here. We have two levels, right? The two levels are like that, E0 minus E, E0 plus E. As I told you, this E0 doesn't matter. It doesn't matter where I draw this thing. But what matters is this gap, delta. And delta here, in my choice of values, here I have chosen E, delta is equal to 2E, the same 2E that appears here. So it's the gap in energy that determines the dynamics, that determines the periodicity. Okay, so in other words, well, and you can call this, well, if you write this omega, right, well, this would be, well, this is, what I'm saying here is that we have an evolution that is I phi of t that is equal to ei omega t with omega equal to 2e over h bar, which is equal to delta over h bar. And this, what is written here, is all that there is to know about the time-independent evolution of a qubit. The rest is to give a relevant physical model for these guys in the case when the qubit is a photon, has a polarization, if it's a spin, if it's a 2 energy levels of an atom, whatever. But all the algebra is done. You can just, whatever physical system you have, it is a qubit, you can copy and paste the solution, it's done here. Now, in the lecture notes, the next part is about a specific time-dependent Hamiltonian that can be solved exactly. So let me just say a few words on that, and then I will, instead of following the equations, I will give you a PowerPoint presentation that tries to convey the physics of it, and the equations you can follow if you want in the lecture notes. Incidentally, the details of the equations will not be tested in the exam. Please don't switch off now. Keep watching. So now we have a time-dependent Hamiltonian. I told you, in general, it's a mess. So, well, but there is one specific time-dependent Hamiltonian that is very useful, and I will tell you where it comes from before going to the PowerPoint presentation. So the one that is very frequent and exactly solvable is the following. There is a time-independent part that we typically write like this for reasons that you will understand. So for this part is a time-independent one. I remove the identity, doesn't matter, and the sigma m is equal to sigma z, and the e, I write h bar omega 0 over 2, which there you see that the gap delta is h bar omega 0. That's my definition of omega 0. On top of this, I will add a time-dependent part that looks like that. may say, well, where does he get that from? Well, first of all, again, this is now the matrix here is sigma x or sigma y. The coefficients are, however, rotating with time. This m here for this part is rotating with time. Right? So you may say, well, where does this come from? Well, this one is used in atomic clocks, in nuclear magnetic resonance, and in many other cases, in atom interferometry, or at least a similar one. The idea behind nuclear magnetic resonance is like this. This one, so let me do the NMR physics. So the idea is that I have a spin in a magnetic field. And what magnetic fields do I have? I have two magnetic fields. I have one magnetic field that is static, B0 in the z direction is static and strong. That's when you go for MRI, I hope you don't, but if you go for MRI, that's the magnet, a permanent magnet where you put your head or your knee into. Permanent magnet, fixed there, usually electromagnet in these things. That's why they have to be cooled. Now, on top of this B0, there is a B1 perpendicular to it, much smaller, and that rotates with frequency omega t in the plane xy. This is the thing in your MRI that makes a noise. Well, there are other things that make a noise. And the idea is that we are going to see how this one, we switch it on and off to create an interesting dynamics, on and off, to create some dynamics on the spin. To understand what I'm going to say, the only thing you need to know, and then we go to the PowerPoint, is you have to remember that, forget about for the moment for B1, if there is a spin, a magnetic moment, around a field like that, it precesses. The dynamic of a spin around the magnetic field is a precession around the effective magnetic field. I'm forgetting about B1 for the moment. Okay? Now, this is my M, is the spin. Well, yes. And this is my static magnetic moment, magnetic field, and this is the varying magnetic field. You see that the components of the magnetic field are rotating. Okay? So this is the physical situation. Now, let me switch on the PowerPoint presentation, and we are going through these in a more qualitative way. I will switch off one light so that you can see better. Okay, coming back. Readjusting the microphone, that fell, of course. Very well, so let's go through this presentation about spin resonance. And again, as I told you, it applies to nuclear magnetic resonance. It also applies to atom interferometry, and not exactly atom interferometry, rather interferometry of atom levels. And these are called Rabi and Ramsey interferometry. I will try to explain to you what is the difference between these two, knowing that we are not going to do detailed NMR in this class, and these things are normally dealt with in atomic physics or in quantum optics, or I think even QM2 they mentioned this. So this is more of an introduction, just to give you some idea of this physical phenomena. So, as I told you, we start with our magnetic moment, the spin. This is the sphere of Bloch vectors. By the way, I forgot to tell you, it's called the Bloch sphere. So now my Bloch vector is pointing in the z direction. Why? Because it is in a strong magnetic field B0. It has a time to thermalize. I left it there for a long time. Thermalization is not something I'm discussing here, but it has equilibrated with the field, and it points in the Z direction. My goal, for some reason, is to try to bring this spin here. I want to flip it. Why? If I flip it here, it rotates. If it rotates, and if I put it in a coil, a magnetic moment changing in time in a coil generates a current. And this current I can detect. Okay? So that's the principle of detection of NMR. You have a magnetic moment rotating. There is a coil out there that's not drawn that picks up the signal and generates an AC current with the suitable properties. But now, how am I going to flip this one? What can I do to take this one down there? Okay, let's try something that doesn't work. You could say, oh, I add a field. So I take that's my situation, and I add a static B1 that will, therefore the total field now is B1 plus B0, and it starts rotating around some direction, right? If B1 is in the X direction, it will rotate towards the Y axis. That is true, indeed. After one step, you will get there. But now, see what happens. B1 is small, and B0 is big. Now, this is a magnetic moment out of equilibrium in a strong magnetic field, is not aligned. What is it going to do? Well, it's going to precess. Right? By the time I see it, it has precessed there. And now, of course, I'm doing a dynamics a little bit piece by piece, but you can do the calculation in general, and it works exactly like this. Now, very fast, because this is very big, the magnetic moment that was in this direction has rotated there. This guy, what does it do? It still rotates like that. This one being a magnetic field in this direction, it always induces a rotation in this sense. But now this guy is on, the magnetic moment is on the wrong direction. So when it rotates back. Again, this is a hand-waving thing, but you see what I mean, is that you have this magnetic moment, you try to bring it out of equilibrium, and as soon as it's out of equilibrium, it starts rotating very fast, and the small field that is trying to keep it out of equilibrium cannot catch up. So yeah, it will move a little bit, but it will stay up there. Here is where the idea of resonance comes into play. That's why it's called nuclear magnetic resonance. The idea is to rotate B1 according to B0. Let me show you how that goes. So the first step is the same. I put my B1, the magnetic moment starts rotating. And there we are. Now, the frequency at which this rotates is given by, in this field, is given by that. So what am I going to do? Well, I'm going to move my B1 back there so that it keeps rotating in the right direction. I move my B1 back there, and now the magnetic moment wants to rotate according to B1. But B1 pointing like this, now it wants to rotate like that. And that's what I want, because it's back there. Right? And you see how it continues. Now, it will rotate. It will be here. It will rotate minus omega t. It will be there. I bring back my B1 here, and I rotate again in the right direction. So the total dynamics, sorry, I didn't generate that with mathematics. I just generated by my hands. It gives this kind of spiraling behavior until indeed it falls where I want. Again, the idea is to rotate my B1 in the plane to follow the evolution, the natural evolution induced by B0. Now, you can also describe this in a much simpler way by putting yourself on a rotating frame, a frame that rotates with B1, and then what you would see is a very nice homogeneous descent from there to here. Okay, that's all what I wanted to say for the PowerPoint. Again, the equations are all written in the lecture notes. Those who are interested, you can read them. Those who are not interested, you can keep them there, remember them maybe when you study quantum optics or atomic physics, because they will come again. With this, I finished chapter 3. This is all the material we need to cover by the recess week. So now what we have to do is to study this material, do the tutorials, come for consultation if you want, and then after the recess week, we will have a test on chapters 2 and chapter 3. Thank you.